Yeah, the video is not working very well, so I don't know. Okay, let's see. So our next speaker is going to talk about nano-coated and nanostructured optical fiber sensors and biosensors, past 3-year perspectives, and he's Mateusz Smietana, our invited speaker. He's doing some research here at the Public University of Navarra, and we have the pleasure of having him here. And please, Smietana, what you want to have the over there.
Okay, thank you very much. Thank you very much for the invitation to organize this seminar with my stay here. So my talk will be about nanocoated, mainly about nanocoated nanostructured sensors. But I wanted to focus on like last 3 years perspective, since I was here almost exactly 3 years ago. Together with my friends, members of my team. So this was the presentation 3 years ago. And so Mateusz, Mateusz, and I was able to be here, and again, thanks to them, I'm here. So I will be mostly talking about the past 3 years perspective, just to the status and the progress. The most interesting difference is there were 3 of us at the time. Now I'm on my own, but it doesn't mean that they are not within my team, they just didn't come. But instead, there is 3 places of work. So currently I'm working in 3 places. One of them is in Czech Republic, and 2 others are in Poland. So members of my team, just preparing the presentations yesterday, I realized that it's highly outdated. Here there is a row of the deposition systems already, so the members of the team are still these, but we have a lot more people. So what we do within the group basically focus on thin films, so on the position, on properties of this image, tuning them to get certain properties, so we can characterize and measure and analyze and so on. Process as well. We do fiber optic sensors, but also electrochemical sensors, other optical sensors based on these thin films, and all that for biosensors. So this is our main purpose. But other members of the Faculty of Electronics and Information Technology, we also develop interpretations. So we have just to serve. Just to give you some examples, the system we developed for industrial purposes is a system that combines chemistry and optics at the same time. Some simpler versions of these, also these based on smartphones, which show you later. And also we develop systems, so something that was not in use for a long time was developed to fully functional system. You can see the deposition taking place here. And sometimes we like to have fun, also left over. So why we like these films? Because the films are essential for getting some sensing effects, SPR, LMR, some cavities, and so on. They can tune the sensitivity. That was especially important when we talk about gradients or some other systems. When the fiber index appears, it can tune the distribution of that field and tune the properties of the system. Some sensitivity reduction can be obtained by using the films. Also, chemical and mechanical protection can be maintained. But what's very important, the coating is a link to biology. So we need to keep in mind always that this is like an interference referential field, so that this will be interacting with biology moves. And also an interesting phenomenon when people are electrically productive and optically transparent, some interesting effects can be obtained, so we can interrogate the system which involved in this dynamic. So one of our premiums is here, so people working there doing different material processing. So in total, we have 5 sputtering systems available. One of them is fully natural, so there's an 8-inch target. This is pure source of material, and there's 4 of them, so we can do sputter, post-sputter, do multi-layers. But we have also smaller system with 2-inch target, it's also for sputtering. We have 2 systems for CVD, so plasma intensity, and that's for deposition, but also can be used for etching. In dry etching, we have system for atomic layer deposition, plasma etching system. So here is like some of the materials we already tried, we already deposited in our lab using some labs of our collaborators. And here you can see maybe here this is a fiber like immersed in plasma. So this is doing this pattern form. And we mainly focus on label-free biosensors. So ladies just before me introduced that quite well, but just to let you know in details. First of all, we need to have a circuit. Then on the surface, there must be some functional lines, biofunctional surface. In one of the presentation, you could see antibodies. So they need to grab, or they are supposed to grab some analyte, target. So that's what we as engineers, as people dealing with the sensor, can do. We can improve this transducer, so improve the sensor itself. But whatever goes above is mostly chemical, biochemical domain, because that's responsible for the systems. So many different transducers were reported up to date. Some commercial devices based on surface plasma resonance, some filter transistors, some cantilevers which oscillates with the change the frequency when the material is. So there's a lot of advantages of these systems. They are fast, they are quite simple because the only thing is functionalization and processing of the surface that is required. And they are universal. You can change the receptor, and then obviously you change the target. But there is a lot of disadvantages. Cross sensitivity is common. Most of the sensors are unfortunately sensitive to temperatures, so they can give exactly the same readout as for identification of some volume. So false positive result. Limited sensitivity, that's something that we need to deal with. When the molecule is too big or too small, it may not be identified by this system, and non-specific findings. So if some target molecules is located in between of the receptors, that's also part of it. So there is a lot of things that we need to work on still up to the moment when this biosensor will be like fully reliable. One of them is to interrogate these sensors within different domains. So interrogate the same sensor at the same time using, let's say, some other means, like electrochemistry in this case, this is electrochemical setup, or electrochemistry plus SPR. So these sensors are somehow reported. One of them was reported on the fiber, but it's quite complex structure. You may see that there's a gradient in the core, it requires fiber processing, and then there must be gold deposited. So quite complex structure, sensitive, but still complex, and in terms of mass manufacturing, it's not. So that's why from the perspective of mass manufacturing, as biosensing, we focus more on some simpler devices. And Thanks to great works of people here, there was a lot of effort put into development of resonance sensors. So we try to work with different materials just to get this lot of momentum. So they are mostly robust materials deposited by sputtering or by plasma within the channel. So even right boron diamond, which is not like the most friendly material ever, because it requires temperature and amplification with the film, but the film is extremely robust and much difficult to store in. So this is like a good thing and a good mechanism that can be used for detections. But the most important thing that when we apply some materials, one of them is indium tin oxide, but there are some other materials that we tell you later. They can be also on top of optical transparency and good properties for LMR that can be also applied. So it can be used as an electrode at the same time. So ITO is one of them, it's an N-type semiconductor, optically transparent. So the piece of the fiber, this multiple fiber, was connected to the light source with transparent configuration, and then stopped by ITO. Electrodes, you can see here 3 electrodes, all of the electrodes. So that's the Warsaw at that time, because ITO seems to be a nice material used for displays, let's say, in phones, on smartphones, you know, for touch screens mostly, provide you as a service. But it's electrically conductive and optically transparent. But when we expect them to work as both electrode and losing of resonance material, it's not that easy. You can see that these are the curves that are supposed to be electrochemically obtained for a good electrode. And they are possible to be obtained for ITO as well. This is for different redox probes, so we can see the peaks of oscillation and reduction. But unfortunately, for the optical readout, it's not that. But when we slightly tune the properties of the ITO, it tends to be good for LMR, but unfortunately not. So there was a lot of effort put to post-processing, to tune the position condition just to satisfy. And why is it so? Because that's N-type semiconductor. So there's charges. This is mean number of charges in accumulation zone in the semiconductor. So you can imagine kind of reference electrical circuit of this device. So there is metal because we connect the ITO somehow. Then there is like interface with the aquarius solution. So this is the aquarius solution. So it's a capacitor actually. It's a metal insulator semiconductor capacitor that we form by application of electrochemical circuit. So in this case, we have ITO obviously on the fiber core, there's the metal contact, and then so it's an equivalent circuit, let's say, or equivalent situation. And when a negative potential is applied, we form here accumulation zone. And when accumulation zone is formed, the refractive index of this region drops. But it drops differently for different accumulation of the free charges in the material. So when we obtain certain material, we need to take care of the number of charges that are there. For electronics, definitely high number of charges. But for optics, unfortunately, low. So just playing with the potential can tune this number of charges in accumulation zone, and we can tune also the ability of the system for being used as an optical. So also in the time we carry different materials. One of them is fluorine oxide. It may work similarly to that, slightly different value. So just very recently, we noticed that this material is actually quite good for laboratory biosensors. So at that time, with ALD, we deposited very thin material on top of the ITO just to simulate the conditions that takes place when the biosensing processes are going. So you can see that when negative potential is applied to the electrode, the refractive index of this thin surface of the ITO drops significantly and then increases. But it drops significantly differently depending on the thickness of the film that is formed on the surface. So this is like a great biosensing principle. The same with imaginary part of the it's like we can putting by polarizing the material, we can tune the ability of the material to identify the field that is formed on the surface. So at first, electrochemically, you can see this oxidation and reduction peaks, then they disappear. But during the modulation, you can see that first we get very deep modulation effect initially, and then it's just get less and less. And this actually the modulation, so tracing this how far you can go into lower wavelength the resonance, can indicate the presence of the molecule. So that's actually quite simple phenomenon because we can apply negative voltage to the electrode and identify what's on the cell. Okay. So we apply a very simple device. That's a smartphone converted into spectrum. There's some adapter, there's some grading side, and there are fibers. Input fiber and output fiber, electrochemical cell, potential starting here. So you can see when you apply voltage, we can monitor the change in transmission. So by applying voltage, we see optically the changes. And when some biomaterial appears on the surface, electrically, obviously, we see it. Yeah? So that's electrical response, and the current increases, but also optical response changes. So with the smartphone, we can optically identify electrochemical interactions in this. What needs to be emphasized is that these currents are relatively small. So with the smartphone, we are not able to identify the small currents, and it's very easy to identify the small. So then we thought, oh, how about improving some other means? Sensing, and one of them is spectral electrochemistry. It's a very well-known method for electrochemistry. So we just shine the light through transparent electrode and detect the changes that appears in the spectrum on the other side, and the changes are related to reactions taking place at the end. So some information about reactants or reaction products can be accumulated by the optical. So both optical and at the same time, but flat is surface is different. So these are different electrolytes that we use. You can see that these peaks appears different in different probes, different electrode materials, but these are also optical. So you can see that the transmission changes differently depending on electrolyte and applied voltage. So why not use the fiber instead of the it's smaller, it may be quite effective, and it does not disturb the change in optical path. So we have the standard configuration electrodes, but instead of the electrodes, one of them is the fiber. So we measure this transmission here for the electrolyte and measure also the response in different places where we can locate the electrode. This time it's a localization on the top, so it's like a probe type, so it's easier to insert it. And these are real, so we can get like standard electrochemical readout, explaining the potential, we see the current changes. we see spectral changes. So spectral changes through the electrolyte. There is diffusion of the electrolyte can be analyzed, and some kinetics of the reaction. But we can also analyze optically the behavior of the electrons, optical electrochemical electrons. Then it's slightly just to change the topic of this optoelectrochemical interaction. In the meantime, we started collaborating with medical labs. This was like very fortunate for me because one of the PhD students, medical PhD students, came to me and wanted to start collaboration. It's very, very good actually opportunity, and we made a use of that. This clinician, so he is a radiologist, so he makes all the radiological experiments, investigation, and so on. So he was interested in putting the fiber into human work. Obviously, it's not easy because we need to perform experiments and so on. But just to start. So we made a review on in vivo sensing of fiber. It turned out that there's many sensing already applied, but most of them are based on some physical interactions. So some pressure, temperature, even during exposure to X-ray and some other, but there's no biosensing available. Why? So there were a lot of attempts actually to drive it, but none of them was really successful. And I believe that the main problem is the number of samples. Because for this biosensing experiment, we need a large number of samples, possibly very similar, not different. And these methods that were proposed up to date are very complex. So one of them is to make some patterning of the surface of the tip of the fiber. It works, but not many times. It can be fabricated and shown as a principle of mass fabrication. It's not possible. Some other processing of the fiber, some of them make the fiber very fragile, so they probably would not work. Something to put inside the fiber, not really. So the requirements from the user point of view are these. They must not be robust, they must be repeatable, so we need to deliver tens of them, hundreds of them, not a single sample, and the manufacturing of the same scale. So there's no possibility for making this in one process 500 sequence. So we need to scale the process, and they must be extremely cheap. Because the biology is on the top, biology is extremely expensive, actually. Okay, so just to show you this, yeah. These are the surface of the optical fibers changed with some thin films, and this is just a sample. Yeah? So we can manufacture here was 6 of them, but I will show you later, and many of them the same way. So we started with many films on the surface. Just thought that this would be some kind of good solution, and it worked. It worked for effective index. It worked for sensing of some biomolecules on the surface, and it's scalable. Many hundreds of the fibers can be processed the same way, so that's good, but not sensitive enough. But quite recently, we decided to make a step backward, to limit the number of layers. So when there's one layer on the fiber, there's covering interferometer. But this interferometer is sensitive to refractive index, so the depth of the speed changes with refractive index, and it shifts towards longer wavelength when something is accumulated on the surface in the layers. But when there is another field of lower refractive index on top of it, we can tune the reflection conditions, so we can make this interference pattern very, very deep. And it started to shift index as well. So we shift to the index, shift to deposition, formation of the biofilm on the surface, and it's deep already. Yeah? So we have a lot of benefits of this this configuration, this fields for the cell. So when we deposit more and more of this secondary field, we see that that we get more sensitive structures to the index, so it's small, but it's shallower. So by analyzing this structure, we analyze the sensitivity volume, so the one that gives refractive index response, and the sensitivity to the position of the field on the surface. So there is a thickness for each material, extremely changes the properties of this device. Unfortunately, it's not that deep, so mostly we need to work in this range where the sensitivity is somehow boosted by this field. And we analyze different materials as an application of this secondary field, and it seems that we can slightly improve the sensitivity to formation of the biofilm on the surface by application of certain materials. The current state is we can fabricate over 500 pieces, 500 sensors per one deposition process with a yield of 95%. What means that we are still within the LPG interrogator range. So it means that there is something that is still operable or can be used. So different materials. And about the biosensing application, we have a similar approach to one of the presented. So these films like titanium and carbon oxides were deposited, then the surface was functionalized chemically to bind antibodies. The aluminum was used to fill the gaps between. So you can see that with this MPO, this inflammatory marker in the human body. So it shifts intensity, and the shift can be monitored in wavelength and in transmission. So very low limit of detection. And the other application of that is heavy metal ion detection. So we functionalize the surface of this structure, this very simple structure, with aptamers, DNA aptamers. These are chains of nucleotides. And they change their orientation, they coil with presence of certain ions. So you can see that the mass is getting closer to the surface when the ions are present. And we see that the concentration of copper ions, we see that the depth of this minimum changes, and also it shifts in weight. And we try different heavy metal ions to this configuration. So right now we work on this microfluidic system just to detect many ions at the same time. And also some other approach, since we have a doctor on board, he was able to print the real scenario of aorta in the human body. Actually, the aorta came from two different patients. So just to make the things complex, one of the patients was like the donor for this part, and the other one was for this part. But this was really more. But just to have all these curvatures and possible problems that appear when you want to get to the brain, because this is a typical way. You get from here to here by probes. So just to just use the fiber. So we are monitoring the optical signal at the different stages of this procedure. X-ray was applied at the same time, and you can see that when we measure the refractive index at the entrance, so when the probe was out of that, it worked well. Then we pushed at different stages. We pushed the probe and still operating. Then outside it was still working. Then we pushed it back and it's still working. So it means that all these curvatures inside the human body in the real case scenario, they are not that much. The performance of the system. Just to give you some overview about some other approaches that we use, this was done mostly with collaboration with my involvement in Lukasiewicz Research Network. This is like a chain of research institutions in Poland. They are mostly the aim of these research institutions is to develop products and for the market. Yeah. So it's something like a belief between the university, the basic science, and the applied science. So within the collaboration, we work on some fibers. So one of them is femtosecond laser processed cavity, the side surface of the fiber. So the micro machining is applied in here. The cavity can be drilled, so it can be made in the surface of the fiber. This is single fiber just to get into the core. Obviously, we can tune the shape of our needs. So when something like this appears and we fill it with liquid, you can see that there is a huge sensitivity to the image. So there's a beam that follows the core still, this part of the core of the state, and the part of it goes through the liquid and the interference by the and the pattern obviously itself can be used for effective indexes, but it's not that interesting. We think that it's more interesting for biosensing. So we reported some approaches for detection of bacteria using sample pages, detecting pages with some antibodies and so on. We also did some DNA amplification in the cavity. So these are the results. So we faster than this amplification is used for and the other is obviously, yes, COVID was there, so we had to focus on COVID as well. So we played with biosensing particles, these are safe particles, these cells. And we were able to identify them as well in the data. So that's kind of interesting approach for many different applications. But one of the most important or interesting application is that we can, inside the cavity, we can locate an electrode. So this is a small electrode that when it goes into the cavity, we can optically monitor the chemical processes. So we can see optically